Linux kernel.
The Linux kernel is a Unix-like operating system kernel used by a variety of operating systems based on it, which are usually in the form of Linux distributions. The Linux kernel is a prominent example of free and open-source software. The Linux kernel is released under the GNU General Public License version 2, GPL v2, plus some firmware images with various non-free licenses, and is developed by contributors worldwide. Day-to-day development discussions take place on the Linux kernel mailing list. The Linux kernel was initially conceived and created in 1991 by Finnish computer science student Linus Torvalds. Linux rapidly accumulated developers and users who adapted code from other free software projects for use with the new operating system. The Linux kernel has received contributions from thousands of programmers.
History.
In April 1991, Linus Torvalds, a 21-year-old student at the University of Helsinki, Finland, started working on some simple ideas for an operating system. He started with a task switcher in Intel 80386 assembly language and a terminal driver. On August 25, 1991, Torvalds posted the following to Compose Minix, a news group on Usenet. After that, many people contributed code to the project. Early on, the MINIX community contributed code and ideas to the Linux kernel. At the time, the GNU project had created many of the components required for a free operating system, but its own kernel, GNU Herd, was incomplete and unavailable. The BSD operating system had not yet freed itself from legal encumbrances. Despite the limited functionality of the early versions, Linux rapidly accumulated developers and users. By September 1991, Linux version 0.01 was released on the FTP server, FTP Funetfi, of the Finnish University and Research Network, FUNET. It had 10,239 lines of code. In October 1991, Linux version 0.02 was released. In December 1991, Linux 0.11 was released. This version was the first to be self-hosted. Linux 0.11 could be compiled by a computer running Linux 0.11. When he released version 0.12 in February 1992, Torvalds adopted the GNU General Public License, GPL, over his previous self-drafted license, which had not permitted commercial redistribution. A news group known as Altos Linux was started, and on January 19, 1992, the first post to Altos Linux was made. On March 31, 1992, Altos Linux became Compose Linux. The X Windows system was soon ported to Linux. In March 1992, Linux version 0.95 was the first to be capable of running X. This large version number jump, from 0.1x to 0.9x, was due to a feeling that a version 1.0 with no major missing pieces was imminent. However, this proved to be somewhat over-optimistic, and from 1993 to early 1994, 15 development versions of version 0.99 appeared. On March 14, 1994, Linux 1.0.0 was released, with 176,250 lines of code. In March 1995, Linux 1.2.0 was released, 310,950 lines of code. Version 2 of Linux, released on June 9, 1996, was followed by additional major versions under the version 2 header. January 25, 1999, Linux 2.2.0 was released, 1,800,847 lines of code. December 18, 1999, IBM mainframe patches for 2.2.13 were published, allowing Linux to be used on enterprise-class machines. January 4, 2001, Linux 2.4.0 was released, 3,377,902 lines of code. December 17, 2003, Linux 2.6.0 was released, 5,929,913 lines of code. Starting in 2004, the release process changed and new kernels started coming out on a regular schedule every 2 to 3 months, number 2.6.0, 2.6.1, up through 2.6.39. On July 21, 2011, Linus Torvalds announced the release of Linux 3.0 gone are the 2.6 less than big new greater than days. The version bump is not about major technological changes when compared to Linux 2.6.39. It marks the kernel's 20th anniversary. The time-based release process remained the same. As of 2013, the Linux 3.10 release had 15,803,499 lines of code.
Tannenbaum-Torvalds debate.
The fact that Linux is a monolithic kernel rather than a microkernel was the topic of a debate between Andrew S. Tannenbaum, the creator of Minix, and Linus Torvalds. The debate, started in 1992 on the Usenet discussion group Compose Minix, was about Linux and kernel architecture in general. Tannenbaum argued that microkernels are superior to monolithic kernels and that therefore Linux is obsolete. Unlike traditional monolithic kernels, device drivers in Linux are easily configured as loadable kernel modules and are loaded or unloaded while running the system. This subject was revisited on May 9, 2006, and on May 12, 2006 Tannenbaum wrote a position statement.
Legal aspects. Licensing terms.
Initially, Torvalds released Linux under a license which forbade any commercial use. This was changed in version 0.12 to the GNU General Public License, GPL. This license allows distribution and sale of possibly modified and unmodified versions of Linux but requires that all those copies be released under the same license and be accompanied by the complete corresponding source code. Torvalds has described licensing Linux under the GPL as the best thing I ever did.
GPL version 3.
Currently, Linux is licensed only under version 2 of the GPL, without offering the licensee the option to choose any later version, and there is some debate over how easily it could be changed to use later GPL versions such as version 3, and whether this is even desirable. Torvalds himself specifically indicated upon the release of version 2.4.0 that his own code is only under version 2. However, the terms of the GPL state that if no version is specified, then any version may be used, and Alan Cox pointed out that very few other Linux contributors have specified a particular version of the GPL. In September 2006, a survey of 29 key kernel programmers indicated 28 preferred GPL v2 to the then current GPL v3 draft. Torvalds commented, "I think a number of outsiders believed that I personally was just the odd man out, because I've been so publicly not a huge fan of the GPL v3.
Loadable kernel modules.
It is debated whether loadable kernel modules, LKMs, are to be considered derivative works under copyright law, and thereby fall under the terms of the GPL. Torvalds has stated his belief that LKMs using only a limited, public subset of the kernel interfaces can sometimes be non-derived works, thus allowing some binary-only drivers and other LKMs that are not licensed under the GPL. A very good example for this is the usage of DMABUF by the proprietary NVIDIA graphics drivers. DMABUF is a recent kernel feature, under GPL, that allows multiple GPUs to quickly copy data into each other's frame buffers. One possible use case would be NVIDIA Optimus that pairs a fast GPU with an Intel integrated GPU, where the NVIDIA GPU writes into the Intel frame buffer when it is active. But, NVIDIA will not be able to use this infrastructure because it is GPL. Alan Cox replied on LKML to a request from one of their engineers to mark the API non-GPL. Not all Linux contributors agree with this interpretation, however, and even Torvalds agrees that many LKMs are clearly derived works, and indeed he writes that kernel modules are derivative by default. On the other hand, Torvalds has also said that one gray area in particular is something like a driver that was originally written for another operating system, that is clearly not a derived work of Linux in origin. That is a gray area, and that is the area where I personally believe that some modules may be considered to not be derived works simply because they weren't designed for Linux and don't depend on any special Linux behavior. Proprietary graphics drivers, in particular, are heavily discussed. Ultimately, it is likely that such questions can only be resolved by a court.
Kernel modules.
Netlink, Network Scheduler, NetFilter and NFTables. Alternatives for other kernels are, for example, PF developed by OpenBSD, NPF developed by NetBSD, comparison of open source wireless drivers, Direct Rendering Manager, Graphics Execution Manager, free and open source device drivers, graphics, Advanced Linux Sound Architecture, free and open source device drivers, audio, EVDOV.
Firmware binary blobs.
One point of licensing controversy is Linux's use of firmware binary blobs to support several hardware devices. These files are under a variety of licenses, many of them restrictive, and their exact underlying source code is usually unknown. In the year 2002, Richard Stallman stated why, in his point of view, such blobs make Linux partially non-free software, and that distributing Linux violates the GPL, which requires complete corresponding source code to be available. In 2008, Free Software Foundation Latin America started a project, Linux Libre, to create a completely free kernel without proprietary objects, which is used by some completely free distributions, such as those endorsed by the Free Software Foundation. On December 15, 2010, the Debian project announced that the next Debian stable version would come with a kernel stripped of all non-free firmware bits. This policy was continued with the sequel release of Debian 7 Wheezy.
Trademark.
Linux is a registered trademark of Linus Torvalds in the United States and some other countries. This is the result of an incident in which William Delacroix, Jr., who was not involved in the Linux project, trademarked the name and subsequently demanded royalties for its use. Several Linux backers retained legal counsel and filed suit against Delacroix. The issue was settled in August 1997 when the trademark was assigned to Linus Torvalds.
SCO litigation.
In March 2003, the SCO Group, SCO, filed a lawsuit against IBM claiming that IBM had violated copyrights that SCO claimed to hold over the Unix source code, by contributing portions of that code to Linux. Additionally, SCO sent letters to a number of companies warning that their use of Linux without a license from SCO may be a violation of copyright law, and claimed in the press that they would be suing individual Linux users. IBM then promised to defend its Linux customers on their behalf. This controversy has generated lawsuits by SCO against Novell, Daimler Chrysler, partially dismissed in July 2004, and AutoZone, and retaliatory lawsuits by Red Hat and others against SCO. In early 2007, SCO filed the specific details of the purported copyright infringement. Despite previous claims that SCO was the rightful owner of 1 million lines of code, they specified 326 lines of code, most of which were uncopyrightable. In August 2007, the court in the Novell case ruled that SCO did not actually own the Unix copyrights to begin with, though the 10th Circuit Court of Appeals ruled in August 2009 that the question of who owned the copyright properly remained for a jury to answer. The jury case was decided on March 30, 2010 in Novell's favor.
Architecture.
Linux is a monolithic kernel. Device drivers and kernel extensions run in kernel space, Ring 0 and many CPU architectures, with full access to the hardware, although some exceptions run in user space, for example file systems based on Fuse. The graphics system most people use with Linux doesn't run in the kernel, in contrast to that found in Microsoft Windows. Unlike standard monolithic kernels, device drivers are easily configured as modules, and loaded or unloaded while running the system. Also, unlike standard monolithic kernels, device drivers can be preempted under certain conditions. This latter feature was added to handle hardware interrupts correctly, and to improve support for symmetric multiprocessing. By choice, the Linux kernel has no binary kernel interface. the hardware is also incorporated into the file hierarchy. Device drivers interface to user applications via an entry in the /dev and/or /sys directories. Process information as well as mapped to the file system through the /proc directory. Linux supports true preemptive multitasking, both in user mode and kernel mode, virtual memory, shared libraries, demand loading, shared copy on write executables, via KSM, memory management, the Internet Protocol Suite, and threading.
Programming language.
The Linux kernel is written in the version of the C programming language supported by GCC, which has introduced a number of extensions and changes to standard C, together with a number of short sections of code written in the assembly language, in GCC's AT&T-style syntax, of the target architecture. Because of the extensions to C it supports, GCC was for a long time the only compiler capable of correctly building the Linux kernel. In 2004, Intel claimed to have modified the kernel so that its C compiler also was capable of compiling it. There was another such reported success in 2009 with a modified 2.6.22 version of the kernel.
Interfaces.
Conformance to standards is a general policy for the Linux kernel's internals.
Kernel to user space API.
Source code portability ensures that a C program written by conforming to a standard can be successfully compiled and run on any system that also conforms to the same standard. The relevant standards, aiming to achieve source code portability of programs, that the development of the Linux kernel, the GNU-C library, and associated utilities tries to adhere to, are POSIX and the single Unix specification. However, as of February 2014, no Linux distributions are branded as Unix by the Open Group, mainly because of the costs of the conformance testing. The Linux kernel API of the Linux kernel, representing the kernel's system call interface, is composed of the available system calls.
Kernel to user space API.
Binary portability shall guarantee that any program once compiled for a given hardware platform, can be run in its compiled form on any other hardware platform that conforms to the standard. Binary portability is an essential requirement for the commercial viability of independent software vendor, ISV, applications built for the operating systems based on the Linux kernel. Binary compatibility is much more demanding than source code portability. As of February 2014, the only standard concerning itself with binary compatibility is the Linux Standard Base, LSB.
In kernel API.
There are a couple of kernel internal APIs utilized between the different subsystems and subsystems of subsystems. Some of them have been kept stable over several releases, others have not. There are no guarantees regarding the in-kernel APIs. Maintainers and contributors are free to augment or change them at any time. Examples of in-kernel APIs include Software Frameworks APIs for the following classes of device drivers. Video for Linux, for video capture hardware, Advanced Linux Sound Architecture, for sound cards, New API, for network interface controllers, Direct Rendering Manager, for graphics accelerators, Mac 80211, for wireless network interface controllers, WEXT, for wireless network interface controllers, obsolete.
In kernel API.
Strong interests in defining and maintaining a stable in-kernel API over several releases have been voiced repeatedly over time by parties, for example hardware manufacturers, writing proprietary kernel modules and distributing binary-only software, for example device drivers. By explicit choice the Linux kernel does not maintain a stable in-kernel API. The reasons are purely technical and not philosophical. Due to the absence of an in-kernel API that has to be kept stable over releases, the Linux kernel can keep a much higher rate of development.
Technical features. Preemption.
The Linux kernel provides preemptive scheduling under certain conditions. Until kernel version 2.4, only user processes were preemptive, that is, in addition to time quantum expiration, An execution of current process in user mode would be interrupted if higher dynamic priority processes entered task running state. Towards Linux 2.6, an ability to interrupt a task executing kernel code was added, although with that not all sections of the kernel code can be preempted. The Linux kernel contains different scheduler classes. By default, the kernel uses a scheduler mechanism called the completely fair scheduler introduced in the 2.6.23 version of the kernel. Internally, this default scheduler class is also known as SCHED-Other, but the kernel also contains two real-time scheduling classes named SCHED-FIFO, real-time first-in first-out, and SCHED-RR, real-time round-robin, both of which take precedence over the default class. Through the use of the real-time Linux patch preempted support for full preemption of critical sections, interrupt handlers, and interrupt disable code sequences can be supported. Partial mainline integration of real-time Linux already brings some functionality to Linux mainline. Preemption improves latency, increases responsiveness, and makes Linux more suitable for desktop and real-time applications. Older versions of the kernel had a so-called big kernel lock for synchronization across the entire kernel. This was finally removed by Arnd Bergman in 2011. Additional scheduling policy known as SCHED deadline, implementing the earliest deadline first algorithm, EDF, was added to the Linux scheduler in version 3.14 of the Linux kernel mainline, released on March 30, 2014.
Portability.
While not originally designed to be portable, Linux is now one of the most widely ported operating system kernels, running on a diverse range of systems from the ARM architecture to IBM's Z architecture mainframe computers. The first port beyond Linux's original 386 architecture was to the Motorola 68000 platform by Amiga users, but to do this port they replaced major parts of the kernel, leading Torvalds to call it a fork and a Unix-like operating system. With this experience in mind, Torvalds led a major restructure of the kernel code to facilitate the next port effort, to the DEC Alpha AXP platform, and support both 386 and Alpha in a single source tree. Linux runs as the main operating system on IBM's Blue Jeans supercomputers. As of June 2013, the Linux OS family has a 95.2% share of all systems on the TOP 500 supercomputers list. Linux has also been ported to various handheld devices such as Tux Phone, Apple's iPod and iPhone. Some operating systems developed for mobile phones use modified versions of the Linux kernel, including Google Android, HP Web OS, and Nokia Memo.
Kernel panic.
In Linux, a panic is an unrecoverable system error detected by the kernel, as opposed to similar errors detected by user space code. It is possible for kernel code to indicate such a condition by calling the panic function located in the header file system H. However, most panics are the result of unhandled processor exceptions in kernel code, such as references to invalid memory addresses. These are typically indicative of a bug somewhere in the call chain leading to the panic. They can also indicate a failure of hardware, such as a failed RAM cell or errors in arithmetic functions in the processor caused by a processor bug, overheating damaged processor, or a soft error.
Kernel oops.
A report of a bug in the kernel is called an oops. These crash reports are automatically collected and can be sent upstream by various software, such as kernel oops, ABRT, Fedora, and a port, Ubuntu. KernelOops.org collected these reports and published statistics on their website.
Security.
Computer security is a much publicized topic in relation to the Linux kernel, because a large number of bugs in the kernel can be potential security flaws, whether they allow privilege escalation or create denial-of-service attack vectors. Over the years, numerous such flaws were found and fixed in the Linux kernel. New security features are continuously implemented to address computer insecurity issues in the Linux kernel. Critics have accused kernel developers of covering up security flaws or at least not announcing them. In response, in 2008, Linus Torvalds replied, "I personally consider security bugs to be just normal bugs. I don't cover them up, but I also don't have any reason whatsoever to think it's a good idea to track them and announce them as something special. One reason I refuse to bother with the whole security circus is that I think it glorifies, and thus encourages, the wrong behavior. It makes heroes out of security people, as if the people who don't just fix normal bugs aren't as important. In fact, all the boring normal bugs are way more important, just because there's a lot more of them. I don't think some spectacular security hole should be glorified or cared about as being any more special than a random spectacular crash due to bad locking." In May 2012, a difference between the implementations of the scissor instruction in AMD and Intel processors was found to cause vulnerabilities in major systems such as Windows, FreeBSD, Xen Server, and Solaris. The issue had been fixed in the Linux kernel since 2006. Raw hardware devices are protected from direct access, and the file system has an inbuilt security system giving individual access to files on 3 levels: user-only, group membership, and world access. Long-term releases with constant security updates are also available for most distributions. Reboot-less security updates can even be applied to the kernel by using technologies such as XSplice.
Feature history.
Version 1.0 of the Linux kernel was released on March 14, 1994. This release of the Linux kernel only supported single-processor i386-based computer systems. Portability became a concern, and so version 1.2, released March 7, 1995, gained support for computer systems using processors based on the Alpha, SPARC, and MIPS architectures. Version 2.0 was released June 9, 1996. There were 41 releases in the series. The major feature of 2.0 was SMP support, that is, support for multiple processors in a single system, and support for more types of processors. Version 2.2, released January 26, 1999, removed the global spin lock and provided improved SMP support, and added support for the M68K and PowerPC architectures as well as new file systems, including read-only support for Microsoft's NTFS. Version 2.4.0, released on January 4, 2001, contained support for ISA plug-and-play, USB, and PC cards. It also included support for the PA RISC processor from Hewlett-Packard. Development for 2.4x changed a bit in that more features were made available throughout the duration of the series, including support for Bluetooth, Logical Volume Manager, LVM, version 1, RAID support, Intermezzo and ext3 file systems. Version 2.6.0 was released on December 18, 2003. The development for 2.6x changed further towards including new features throughout the duration of the series. Among the changes that have been made in the 2.6 series are, integration of Linux into the mainline kernel sources, PAE support, support for several new lines of CPUs, integration of ALSA into the mainline kernel sources, support for up to 232 users, up from 216, support for up to 229 process IDs, 64-bit only, 32-bit Arch is still limited to 215, substantially increased the number of device types and the number of devices of each type, improved 64-bit support, support for file systems which support file sizes of up to 16 terabytes, in kernel preemption, support for the native POSIX thread library, NPTL, user mode Linux integration into the mainline kernel sources, Selinux integration into the mainline kernel sources, InfiniBand support, and considerably more. Also notable are the addition of several file systems throughout the 2.6x releases, Fuse, JFS, XFS, ext4 and more. Details on the history of the 2.6 kernel series can be found in the changelog files on the 2.6 kernel series source code release area of kernel.org. Version 3.0 was released on July 22, 2011. Torvalds announced that the big change was nothing. Absolutely nothing. May 30, 2011 saw Torvalds announce, "Let's make sure we really make the next release not just an all-new shiny number, but a good kernel too." After the expected 6 to 7 week development process, it would be released near the 20th anniversary of Linux. In December 2012, Torvalds decided to reduce kernel complexity by removing support for i386 processors, making the 3.7 kernel series the last one still supporting the original processor. The same series unified support for the ARM processor. Version 3.11, released on September 2, 2013, adds many new features such as new OTMPL flag for Open, 2, to reduce temporary file vulnerabilities, experimental AMD Radeon dynamic power management, low latency network polling, and ZSWAP, compressed swap cache.
Development.
The kernel changes made in year 2007 have been submitted by no less than 1,900 developers, but there may be a lot more because developers working in teams usually count as one. It is generally assumed that the community of Linux kernel developers is composed by 5,000 or 6,000 members. As of 2013, the 3.10 release of the Linux kernel had 15,803,499 lines of code. Without a smart project management, it would not be possible to keep such scale of development up and going. Instead of a roadmap, there are technical guidelines. Instead of a central resource allocation, there are persons and companies who all have a stake in the further development of the Linux kernel, quite independently from one another. Linux is evolution, not intelligent design. Linus Torvalds, 2005. The fact is, evolution often does odd and suboptimal things exactly because it does incremental changes which do not break at any point. It would be next to impossible to manage and coordinate all the development going on, to achieve set goals at set deadlines. Instead, there are incremental changes, that by definition do not break at any point. As a result, any released version of the Linux kernel is fully usable, even if, for example, device drivers do not support all features of the hardware they are written for. The conceptual architecture of the Linux kernel has proved its success. Essential factors for this success were the provision for the organization of developers, and the provision for system extensibility. The Linux kernel's architecture was required to support a large number of independent volunteer developers. This requirement suggested that the system portions that require the most development, the hardware device drivers and the file and network protocols, be implemented in an extensible fashion. The Linux kernel's architecture chose to make these systems extensible using a data abstraction technique. Each hardware device driver is implemented as a separate module that supports a common interface. In this way, a single developer can add a new device driver, with minimal interaction required with other developers of the Linux kernel. The success of the kernel implementation by a large number of volunteer developers proves the correctness of this strategy. Another important extension to the Linux kernel is the addition of more supported hardware platforms. The architecture of the system supports this extensibility by separating all hardware-specific code into distinct modules within each subsystem. In this way, a small group of developers can implement a port of the Linux kernel to a new hardware architecture by re-implementing only the machine-specific portions of the kernel.
Estimated cost to redevelop.
The cost to redevelop the Linux kernel version 2.6.0 in a traditional proprietary development setting has been estimated to be $612 million USD, EU €467 million, PS 394 million GBP, in 2004 prices using the Kokomo man-month estimation model. In 2006, a study funded by the European Union put the redevelopment cost of kernel version 2.6.8 higher, at EU €882 million, $1.14 billion USD, PS 744 million GBP. This topic was revisited in October 2008 by Amanda McPherson, Brian Profite and Ron Hale Evans. Using David A. Wheeler's methodology, the estimated redevelopment of the 2.6.25 kernel now costs $1.3 billion, part of a total $10.8 billion to redevelop Fedora 9. Again, Garcia and Alonso de Magdaleno from University of Oviedo, Spain, estimate that the value annually added to kernel was about 100 million European euros between 2005 and 2007 and 225 million European euros in 2008. It would cost also more than 1 billion EUR, about $1.4 billion US dollars, to develop in the European Union. As of January 4, 2011, using current LOC, lines of code, and wage numbers with David A. Wheeler's calculations, it would cost approximately 3 billion US dollars, about 2.2 billion European euros, to redevelop the Linux kernel.
Development model.
The current development model of the Linux kernel is such that Linus Torvalds makes the releases of new versions, also called the vanilla, or mainline kernels, meaning that they contain the main, generic branch of development. This branch is officially released as a new version approximately every 3 months, after Torvalds does an initial round of integrating major changes made by all other programmers, and several rounds of bug fix pre-releases. In the current scheme, the main branch of development is not a traditional stable branch, instead it incorporates all kinds of changes, both the latest features as well as security and bug fixes. For users who do not want to risk updating to new versions containing code that may not be well tested, a separate set of stable branches exist, one for each released version, which are meant for people who just want the security and bug fixes, but not a whole new version. These branches are maintained by the stable team, Greg Kroch-Hartman, Chris Wright, and others. The development model for Linux 2.6 was a significant change from the development model for Linux 2.5. Previously there was a stable branch, 2.4, where only relatively minor and safe changes were merged, and an unstable branch, 2.5, where bigger changes and cleanups were allowed. Both of these branches had been maintained by the same set of people, led by Torvalds. This meant that users would always have a well-tested 2.4 version with the latest security and bug fixes to use, though they would have to wait for the features which went into the 2.5 branch. The downside of this was that the stable kernel ended up so far behind that it no longer supported recent hardware and lacked needed features. In the late 2.5x series kernel, some maintainers elected to try and backport their changes to the stable series kernel, which resulted in bugs being introduced into the 2.4x series kernel. The 2.5 branch was then eventually declared stable and renamed to 2.6. But instead of opening an unstable 2.7 branch, the kernel developers decided to continue putting major changes into the 2.6 branch, which would then be released at a pace faster than 2.4x but slower than 2.5x. This had the desirable effect of making new features more quickly available and getting more testing of the new code, which was added in smaller batches and easier to test. As a response to the lack of a stable kernel tree where people could coordinate the collection of bug fixes as such, in December 2005 Adrian Bunk announced that he would keep releasing 2.6.16y kernels when the stable team moved on to 2.6.17. He also included some driver updates, making the maintenance of the 2.6.16 series very similar to the old rules for maintenance of a stable series such as 2.4. Since then, the stable team had been formed, and it would keep updating kernel versions with bug fixes. In October 2008 Adrian Bunk announced that he will maintain 2.6.27 for a few years as a replacement of 2.6.16. The stable team picked up on the idea, and as of 2010 they continue to maintain that version and release bug fixes for it, in addition to others. After the change of the development model with 2.6x, developers continued to want what one might call an unstable kernel tree, one that changes as rapidly as new patches come in. Andrew Morton decided to repurpose his tree from memory management to serve as the destination for all new and experimental code. In September 2007 Morton decided to stop maintaining this tree. In February 2008, Stephen Rothwell created the Linux Next tree to serve as a place where patches aimed to be merged during the next development cycle are gathered. Several subsystem maintainers also adopted the suffix next for trees containing code which is meant to be submitted for inclusion in the next release cycle. As of January 2014, the currently in development version of the Linux kernel is held in an unstable branch named Linux Next.
Relation with Linux distributions.
Most Linux users run a kernel supplied by their Linux distribution. Some distributions ship the vanilla, and/or stable kernels. However, several Linux distribution vendors, such as Red Hat and Debian, maintain another set of Linux kernel branches which are integrated into their products. These are by and large updated at a slower pace compared to the vanilla branch, and they usually include all fixes from the relevant stable branch, but at the same time they can also add support for drivers or features which had not been released in the vanilla version the distribution vendor started basing their branch from.
Maintenance.
While Linus Torvalds supervises code changes and releases to the latest kernel versions, he has delegated the maintenance of older versions to other programmers. Major releases as old as 2.0, officially made obsolete with the kernel 2.2.0 release in January 1999, are maintained as needed, although at a very slow pace.
Revision control.
The Linux kernel source code used to be maintained without the help of an automated source code management system, mostly because of Linus Torvalds' dislike of centralized SCM systems. In 2002, Linux kernel development switched to BitKeeper, an SCM system which satisfied Linus Torvalds' technical requirements. BitKeeper was made available to Linus and several others free of charge, but was not free software, which was a source of controversy. The system did provide some interoperability with free SCM systems such as CVS and Subversion. In April 2005, however, efforts to reverse engineer the BitKeeper system by Andrew Tridgell led Bitmover, the company which maintained BitKeeper, to stop supporting the Linux development community. In response, Linus Torvalds and others wrote a new source code control system for the purpose, called Git. The new system was written within weeks, and in 2 months the first official kernel release was made using Git. Git soon developed into a separate project in its own right and gained wide adoption in the free software community.
Version numbering.
The Linux kernel has had 3 different numbering schemes. The first scheme was used in the run-up to 1.0. The first version of the kernel was 0.01. This was followed by 0.02, 0.03, 0.10, 0.11, 0.12, the first GPL version, 0.95, 0.96, 0.97, 0.98, 0.99 and then 1.0. From 0.95 on there were many patch releases between versions. After the 1.0 release and prior to version 2.6, the number was composed as ABC, where the number A denoted the kernel version, the number B denoted the major revision of the kernel, and the number C indicated the minor revision of the kernel. The kernel version was changed only when major changes in the code and the concept of the kernel occurred, twice in the history of the kernel, in 1994, version 1.0 and in 1996, version 2.0. Version 3.0 was released in 2011, but it was not a major change in kernel concept. The major revision was assigned according to the traditional even-odd system version numbering system. The minor revision had been changed whenever security patches, bug fixes, new features or drivers were implemented in the kernel. In 2004, after version 2.6.0 was released, the kernel developers held several discussions regarding the release and version scheme and ultimately Linus Torvalds and others decided that a much shorter time-based release cycle would be beneficial. For about 7 years, the first 2 numbers remained 2.6, and the third number was incremented with each new release, which rolled out after 2 to 3 months. A fourth number was sometimes added to account for bug and security fixes, only, to the kernel version. The even-odd system of alternation between stable and unstable was gone. Instead, development pre-releases are titled release candidates, which is indicated by appending the suffix LC to the kernel version, followed by an ordinal number. The first use of the fourth number occurred when a grave error, which required immediate fixing, was encountered in 2.6.8 SNFS code. However, there were not enough other changes to legitimize the release of a new minor revision, which would have been 2.6.9. So, 2.6.8.1 was released, with the only change being the fix of that error. With 2.6.11, this was adopted as the new official versioning policy. Later it became customary to continuously backport major bug fixes and security patches to released kernels and indicate that by updating the fourth number. On May 29, 2011, Linus Torvalds announced that the kernel version would be bumped to 3.0 for the release following February 6, 39, due to the minor version number getting too large and to commemorate the 20th anniversary of Linux. It continued the time-based release practice introduced with 2.6.0, but using the second number, for example 3.1 would follow 3.0 after a few months. An additional number, now the third number, would be added on when necessary to designate security and bug fixes, as for example with 3.0.18. As of March 30, 2014, the latest stable version is 3.14. The major version number might be raised to 4 at some future date. In addition to Linus's OC development releases, sometimes the version will have a suffix such as tip, indicating another development branch, usually, but not always, the initials of a person who made it. For example, CK stands for Concalivers, AC stands for Alan Cox, etc. Sometimes, the letters are related to the primary development area of the branch the kernel is built from. For example, WL indicates a wireless networking test build. Also, distributors may have their own suffixes with different numbering systems and for backports to their enterprise, that is stable but older, distribution versions.
Variants.
A couple of variants of the Linux kernel exist. Linux Libre, Compute Node Linux, Cooperative Linux, Inc., Operating System, L4 Linux, MK Linux, Root Linux, User Mode.